do the last part, which shouldn't be too bad. So if we drew a picture, well, I just want to drew a picture of this one. The whole, this part is all about Henry's law, and Henry's law says that the solubility of a gas that you dissolve in the liquid is equal to Henry's law constant times, times the partial pressure of that gas above the headspace where you're trying to dissolve it into, okay? So remember I said that sometimes you can calculate Henry's law constant from the information given. That's exactly what we're going to do here. We kind of have two different conditions. It says the solubility of nitrogen gas in water is a certain molarity at 0 degrees Celsius. And then it says that it's going to go ahead, let's see, at the pressure of 0.79 atmospheres. And then it says we're going to jack up the pressure to, instead of 0.790, it's going to be 1.1 atmospheres. So will the solubility increase or decrease? Increase, exactly. So what we're going to do basically is to use the first bit of information to knock out a KH. Okay, Henry's law constant for nitrogen at that temperature, and then we're going to apply it to the second one. That's all it is. Okay. So Henry's law, and this is on your equation sheet, I guess, that you're going to get for Thursday's test. So if you have any last minute questions about, because you guys should be working on those questions at the end of the chapter and stuff. I do have some office hours tomorrow and such. I'll be around, or Wednesday after class, or even Thursday before the test. Wait, Thursday before the test I have a lab. So if it's before the test, like, my lab starts at 10. So I have to come before that on Thursday. So we can rearrange this to solve for Henry's law constant, and it looks like this. So Henry's law constant is the solubility of the gas divided by the partial pressure of the gas above that liquid. This would be the soda pop. So in this case, given the information in the first case, we had a molar solubility of 0.00841 moles per liter of nitrogen at a headspace pressure of 0.790 atmospheres. Round to 3 sig figs, we get 0.00104. As like we talked about on Friday, units would be molarity per atmosphere or pressure. In this case, we'll take molarity and break it out into moles per liter per unit's atmosphere. So then, all we got to do is, the next problem, we're going to use that as our KH, and we have the new partial pressure, solve for the solubility of the gas. So it looks like this. The solubility of nitrogen, C sub N2, nitrogen gas. Henry's law constant, we calculated 0.00104 units are moles per liter atmospheres. The new pressure, increased pressure, is 1.10 atmospheres. Units of atmospheres cancel. We're left with units of moles per liter, which is great. 2 sig figs gives us, 3 sig figs, sorry. 3 sig figs gives us 0.00114 moles per liter. And that's perfect. And it did increase between the two. Dun, dun, dun. So these will be due on Wednesday. And on to part 15. Woo! Should look like this. We're going to revisit this, let's see. A colligative property is one, sounds like a good definition thing to ask about, doesn't it? A colligative property is one that depends only on the number of particles. It doesn't depend on what the particle is. Colligative properties. And we said that boiling point elevation and freezing point depression are colligative properties. Depends only upon the molality of the solute, not what it is. Well, here's the deal. Let's see what When we talk about ionic compounds, we're going to see some examples of ionic compounds. An ionic compound has what? A metal and a non-metal joined together, right? And when you crisscross, you get a neutral formula unit. And when the thing breaks apart then, on the product side of it, what we see ionizes or dissolves in water, it gives you multiple particles. So at the crux of this discussion is basically when it gives you multiple particles, then you get more what I call bang for your buck or whatever, when one piece breaks apart into 2 or 3 or 4 pieces. That's just it. So it's going to be the number of dissolved particles, ultimately, that makes the boiling point elevated, the freezing point depressed. Electrolytes are kind of related to the discussion of ionic compounds, dissolving ionic compounds. So ionic compounds separate in water into their anions and cations. And as such, they are pretty darn good at, if they're swimming around in water, they will support an electrical current flowing through that water. That's what electrical conductivity means. They're called electrolytes then. If you dissolve sugar in water, it's not going to support electricity. If you dissolve sodium chloride in water, it will support the conductance of electricity. I think I might have said before that, like in pure water, you really can't electrocute yourself in pure water. It's the impurities in the water that allow a path for electricity to flow. Ethanol, and this is trying to kind of show you the green blobs don't mean a whole lot other than ethanol is going to stick together. Okay, ethanol doesn't ionize. So here we have this thing's plugged in. It looks dangerous if you ask me. It's plugged in and it's supplying. It's trying to potentially complete a circuit here where electrons, in order for the light to glow, electrons need to flow through here where it's negative to the positive to go ahead and stimulate that little filament to glow. Okay, so the light bulb's not glowing. Now, in this case, we've taken potassium chloride and dissolved it in water. And this, I just think these images are weird. You know, little green blobs, and potassium doesn't look like, neither does chlorine look like that. But of course, the chloride ion is negatively charged. The potassium ion is positively charged. But this actually allows for the flow of electricity between the two panels. Completes the circuit and the light bulb, ta-da! Later on in Chem 2, we're going to be talking more about how strong acids are. Okay, HCl is a very strong acid. Okay, acetic acid is moderately strong. Acetic acid. Well, how would you compare kind of the strengths of those flows from the potassium chloride to the acetic acid? Acetic acid is weaker, exactly. So what that means is actually, or not what it means, but it's related to the fact that when you take acetic acid, you dissolve it in water, it doesn't all break apart. Only part of it breaks apart. We'll be talking about that's kind of what weak acids like acetic acid do. But definitely we got a glow here, or we didn't have a glow with ethanol, because ethanol doesn't ionize at all. Acetic acid ionizes to a lesser extent, or to a certain extent. And potassium chloride, I'm out of here. Maybe ionizes completely. Okay, so, for example, I said you get more bang for your buck, and we're going to kind of look at experimentally the implications. So, you would think that if we get two particles, if we get two particles, that its colligative push would be twice as great as just sugar, compared to sugar. Sugar, you dissolve in water, you get one particle. Sodium chloride, you dissolve in water, you get two particles. So it should depress the twice as much. That makes sense. All right, calcium nitrate. That means that this little 2 here means we get 2 nitrates. So over here, we have 1 calcium cation and 2 nitrate ions. So 3. Thrice. Okay, here in a minute we're going to actually kind of see that only if the solution is pretty darn dilute do we actually get our threefold. Okay? So this is kind of cute. It's got the solid crystal, potassium chloride crystalline structure, and I like it because she has cute little water molecules lifting off the anions and lifting off the cations. But from what we know about water, remember we talked about how the oxygen is partially negative, The oxygen is partially negative, the hydrogens are partially positive. So that's why you kind of see these chlorines surrounded by the hydrogens, okay, and the potassium surrounded by the oxygen. Is that kind of available? This is kind of a dissolving process of potassium chloride. So this is the sort of problem you might run into. Let's say that we make these solutions, aqueous solutions, we're going to make them 0.10 molal, and see which one would have the highest boiling point temperature. Now, highest boiling point temperature. If you're like me, there's some things in science that I don't memorize things, but I just boiling point elevation, freezing point depression. Boiling point elevation just rolls off the tip of my tongue. So when we have the greatest effect with regard to this colligative property we've been talking about, particulates, then we're going to have the highest boiling point. Does that make sense? So just eyeballing them before we do the next slide, which one looks like for each particle you dissolve, you're going to get the highest buck in your back? The first one? Now that's sugar. That's not going to ionize. Does that change your answer? Think it's the third one? Oh wait, I think it's the third one, or fourth one, too. Anything else is the other one? It's three.
Yeah, I'm trying to think of the electron charge on the aluminum.
It's a +3, yeah.
Oh.
Why this one?
Because it's +3 and -3. Right? So you're getting those. CA is only a +2.
And it's the number of particles over here. So this is going to split up and give you an Al +3 and 3 Cl minuses. Right? And this guy isn't going to ionize at all. And this guy's going to give you 2. Then how many is this guy going to give you? So, yeah, I didn't mean to put you guys on the spot, but that first one, that one's glucose, that's sugar. It's not ionic, and it will stay, it'll dissolve, but it'll be just like one cute little blob molecule floating around. So you get $1 for your magnet. Here, you get $2 for your magnet. Here you get 3, and here you get 4. So we kind of think of these on the product side as it ionizes. These would be like stoichiometric coefficients, wouldn't they? Kind of like the number of particles you get back. So that last column in blue is saying what kind of the effective molality you would think it would be, or the real molality of the particles. It's 0.1 molal, then it would be 0.2 molal for sodium chloride, 0.3 molal for calcium chloride, and 0.4 molal for aluminum chloride. So which one would you use, which one would be most effective to spread on to make salt melt away? Mm-hmm. Yep, freezing point depression, boiling point elevation should be the best for aluminum chloride. So not all ionic compounds are created equally, because when they ionize, they give you particles, and it's the particles just more particles. Yep. So the aqueous solution of aluminum chloride will have the highest boiling point and the lowest freezing point. The thing that doesn't ionize, the glucose, C6H12O6, will be least effective. And if it's least affected, that means it's going to have the lowest, just be like kind of like a normal boiling, or maybe, I guess it would be some boiling point elevation, wouldn't it? Yeah. But have the lowest boiling point elevated boiling point, and it'll have the highest depressed freezing point, if that makes sense. So there will be some elevation and depression, but it will just be less compared to aluminum chloride. Note that they'll all be different than regular water because we do have that colligative property working. So sometimes is there lots of work to put in? Okay. Yeah, I think so too. So I think I mentioned that kind of the blue, the 0.1, 0.2, 0.3, 0.4 molar, that is like an ideal sort of effective molality. But what happens actually, like this says, is the more concentrated your solution, then the ionic compound that was dissolved, the cation and the anion start to kind of find each other, and they quit being independent particles. Okay, so at higher concentrations, for instance, you kind of see that even though we have this, the word is solvated, even though we have this potassium chloride in solution, actually the potassium, the plus, and the chloride kind of find each other, and they blob together, basically, and it kind of reduces effectiveness in being independent. So at higher concentrations, that's what we have. And I have a slide to kind of show you. We can see that with just not as an effective boiling point elevator or freezing point depressor. So to see kind of what we think it should be versus what it is, it's called the Van Hoff factor, and it's a lowercase I for the Van Hoff factor. So it's just a simple ratio. This down here, the moles of formula units dissolved, that is what you got from the equation. So the moles of formula units dissolved. So, wait, is that right? Well, I think it's, I'll show you what. So, okay. So, for instance, see, that definition throws me off. But see what we think about this. HCl will dissolve, okay, give you two particles, right? The predicted Van Hoff factor is 2, right? What was observed or measured was 1.9, so a little reduced. Now, this is all relative to a 0.050 molal solution of, in this case, HCl. Okay. So in other words, we didn't quite get the independence of particles that we were after. Okay. Sodium chloride, same thing. Similar measured Van Hoff factor. Magnesium sulfate, same thing. Oh, check this out. Not quite what we thought. Again, we expected 2, but we got 1.3.
So does that mean like the 1.9 and the 1.3 are like averages of how many actually are separate?
Yes.
And some of them are still clumped together,
exactly.
so that it throws it off. Okay.
Exactly. Some of them are clustered together. And what I think, and I didn't track this down, but if you compare the difference between sodium chloride and magnesium sulfate is magnesium sulfate has a charge of 2. plus 2 and make it plus and minus 2. And there's actually more of an attraction when you kind of see that rolling together. Magnesium chloride, you would expect, observe 2.7. Iron 3 chloride, you would expect 4. Observe 3.4. Glucose, how do you know this one? No. What do you think glucose? It's not a metal, it's not ionic. Okay, it's 1. It's like, oh, look at it there. Anyway. Okay. Now this is interesting, I think. For these 3 salts, you're going to see a cross going from more concentrated to less concentrated. So you would expect sodium chloride to have what? 2, magnesium sulfate to have 2. How many should lead 2 nitrate have? 3, yeah. So it's off. Again, this is pretty concentrated. We went from 0.05 molal to 1 molal. Okay? So from 1 molal to 0.1 molal, what do you see the trend in the Van Hoff factor? No. 0.01? 0.001? It's getting better. Okay? And again, we're getting it more and more dilute, so there's more and more water to go ahead and to solvate the cation and anion independently. And so infinite dilution, you would expect the Van Hoff factor to go ahead and be the nominal value. So see what you can do with these. Number 2 of these. I'll double check, make sure. Because anyway, I'll double check they're out there. It would have been several months ago, but anyway, we do Wednesday. I'll hurry over to my desk and see if I got them. If I don't have them, then just do your best. So that's as far as I want to get today, and then on Wednesday we will go ahead and ease into Unit 2 material a little bit. If anybody can find out a good way to review it, I can't think of a good way to review it. No, you're good.
I was gonna say, is there a lot of homework in the first bits, like in the first couple of classes of Unit 2 while we're studying the exam at the same time?
No, there'd just be 1 day overlap anyway.
Okay, great.
Yeah.
Okay, I'm with.
I say ease in, I try to avoid that. You don't see they're out there? I saw them, but I might be crazy, but I saw part 16 too.
I saw part 16.
Yeah, part 16, so I don't know. I wonder if that was my
Missing one.
Remember? Oh, yeah, that makes sense. Part 6, you missed part 16.
Oh,
Okay.
16.
There it is.
That's
Yeah.
magical.
The mystery might be solved. Maybe I should go with it. Thanks. Yeah, this is 1/6. Okay.
You know, I got hired by the Bureau of Commerce to do census work at 2010. And they called me up and they hired me again to just do all the time census work. So I'm with the National Health Institute's
Okay.
survey. And the cool thing is,